Alright, so what I'm going to do here is to give you a summary of what we all discussed and how it all fits together. Because I am aware that Lesson 2, Gradient Descent and Optimizers, is rather difficult in terms of math, as well as there's a lot of new concepts to understand. Yeah? So, just as a summary, we started with a regression problem. Remember, my friend asked me to predict the value of his house. Yeah? So, I put the price and the size of the houses together and would assume that there's a linear model between size and price, and this makes sense. But when I looked at all the houses sold in the neighborhood of my friend's house, and I put these 6 houses in the graph, I saw that I cannot connect these 6 points with a straight line. Yeah? So we were then looking for the best line. If it cannot be the perfect line, let's look at the best line. And in order to do that, we defined a cost function. Yeah? A cost function that would actually give us a penalty when the true y is not equal to the predicted y. Yeah? And this is the cost function we found. We call this the mean squared error. And this is the error. That's the difference between the y on the red line and the y at this point. And we square that. We square it because it's convenient and because we want to penalize outliers. And we divide by m. And m, remember, is the number of training samples. In this case, m was 6. No? M was 6. Okay? Now we have the cost. And what we want to do with this cost, we want to minimize the cost. Yeah? And to minimize the cost, we need an algorithm called gradient descent. Now, what is gradient descent? Well, it's very simple. If you take the parameters w, or the weights on the x-axis, and you have the cost on the y-axis, gradient descent is just a man walking downhill. So you're at a certain point, and you calculate the gradient, and you take the way of the steepest descent. And you do that a numerous amount of time until you reach the minimum. Yeah? The minimum of the cost function, which is basically here. Yeah? This gives you the minimum cost. Right? Call this the cost W minimum. And this here is W minimum. This stepping downwards, we can reflect in an update rule. So we start here, we calculate the gradient in that point. Yeah? The gradient is negative. That means we're in the right direction, and we take a step. Yeah? And this is how you update every iteration until you reach W minimum, or until you reach a point where your cost is barely changing. Yeah? So this was in the univariate case. We have a derivative here. If we look at multiple features, meaning the price of the house not only depending on the size but also on other factors, the only thing that changed is that we take the gradient instead of the derivative. This alpha we have here, alpha is the size of the step you take downwards. Yeah? This is called the learning rate, and that's a hyperparameter, meaning the data scientist needs to choose. Alpha cannot be too small. When alpha is too small, it will take you forever to get down to the minimum. And alpha cannot be too large, because otherwise you will step from one side to the other and you will basically oscillate and not converge. Okay, so that was gradient descent. Now, how can we make gradient descent better? People have been looking to optimize gradient descent because, to be honest, we looked at 6 training samples, whereas in machine learning you can have 300 million training samples. So there is some computation to do, especially because all these weights are updated simultaneously, yeah, at every iteration. So how can we make gradient descent better? Well, the first thing we did, we looked at Newton's method. And Newton's method takes the second order derivative, which is the Hessian, into account. So there's no alpha to choose here. The convergence is definitely faster. And we usually will use it when the number of features is below 1,000. Yeah. Then we looked at Edegrad and RMS prop. The key here is that you will decay the alpha. So you will divide alpha by a certain term. And we've seen that in Edegrad and RMS prop, the term is basically the square of the gradients. Yeah? So every iteration you remember and add up the square of the gradients of the past, bringing this alpha down. Yeah? And that's something we want. And in the beginning you want to take a large step, but if time goes along, you want your step to be smaller and smaller and smaller as you converge to the minimum. Why is that? Well, in this case, you want alpha small. Yeah? But in this case here, you want alpha large. Yeah? Because if alpha is too small, it will take you longer to converge. Yeah? So this Edegrad RMS prop is an algorithm that is decaying alpha using this term. Yeah. Then we looked at momentum and a variant of momentum called Nesterov. Yeah. Momentum allows you to survive local minima, and basically you can compare it with the ball you release. It goes into a local minimum, but because of the inertia it gets over it. The same for this one, yeah? Because the ball gains speed with time. It will get stuck in this global minimum here, but it will also overshoot because of the speed the ball has. Now we can limit the amount of overshoot by applying the Nesterov technique, which we discussed. Now it would be great if we would combine, meaning we will have an alpha decay and have momentum. And that's basically what Atom is. Yeah? Atom is a combination of momentum and RMS prop, and it's widely used. You want to remember RMS prop and Atom. These are the things we will use in our coding exercises. And then as a last thing, we showed that it's convenient to scale features. Yeah? You cannot have, I would say, a range of features from 0 to 5x1. For example, the number of rooms in a house versus a variable from 0 to 20,000. That is the size of the house in square feet. Yeah? So basically what you do, you normalize. It will save you a lot of time, it will converge faster. The way to normalize it, you subtract the mean and you divide by the variance. Yeah? That's how you do. So you have basically data centered around 0 and with a variance of 1. Yeah. Okay, that was it for lesson 2, gradient descent and optimizers. One more thing, remember function can be convex and non-convex. We prefer convex because then the minimum is the global minimum. When it's not convex, it's a bit more challenging. Yeah? So next lesson we're going to discuss classification as well, mainly classification KPIs. Yeah? So we'll leave regression for what it is for the time being and move to classification. See you next time.